Welcome back. Our next learning module is on this topic of arrays in C. And I think it's a pretty fun topic because while syntactically it's not that complex to be able to declare and access arrays, the type of programs we're going to be able to write in C with our knowledge of arrays are going to be way more powerful than what we were able to do previously. Let's dive right in. An array in C is nothing more than just a collection of two or more memory cells that are associated with a single variable name. Syntax is relatively straightforward. We declare the type, we declare a name for the variable, and then we declare how many of memory cells we want to be associated with that same variable name. So here we have x is the variable name, double is the type of that variable. That could be our int, that could be our char, that could be our float, but in this example is double. And 8 then in the brackets is declaring here's how many variables of that type we want to declare at one given time. So for the single name x, that now gives us 8 doubles to work with in our program. To then actually access either reading or writing the contents of that array, we subscript the array. And that just means we provide, again in brackets, which element inside that array we're actually interested in accessing. This works for reads, this works for writes. So it can be either on the left-hand side of an assignment statement or on the right-hand side of the assignment statement. It can be in a relational operator, it can be in a function argument. It is then treated, after we've done that subscripting, as any individual variable of that particular type that we declare the array for. We are eventually going to be talking about pointers in this class, and they are very closely coupled concepts, but we'll get to pointers a little bit more slowly, and we won't see exactly why they're closely coupled until we get to that topic. There are methods for doing what's referred to as dynamic memory allocation, in which at runtime we determine how long we would like our arrays to be. We will learn how to do that eventually, and when we talk about pointers, but for now and for many of the programs we're going to be interested in writing, doing so-called static memory allocation or compile time memory allocation is going to be sufficient for our purposes. Again, static or compile time is referring to the same thing. That is, we have a length of an array that at the time we're writing our program and we hit compile on that program, it is set at that point versus at some time in the future while the program is running determining that would be dynamic or runtime allocation of an array. So for our programs, we're going to be setting these arrays and declaring these arrays via some fixed compile time length. You can use this pound define feature in C to give your code a little bit more flexibility. We haven't been doing a lot of that yet, but this is just an example of another preprocessor macro. We've seen the pound include, which literally means take this file and include it as a header for your own file. Pound define is very similar concept. It's almost like a copy and paste request. We're literally saying and telling the compiler, every time you see the capital word length in this example, replace it with the number 5 in your code. And so you can write your code under the assumption that everything is operating via this variable or this concept of length, but when it's actually compiled, all those lengths, and literally the keyword length it sees in the code, will get replaced with that number 5. So that is still static or compile time length allocation for our arrays, but it gives us a little bit more flexibility in our code. I could write code that works on an arbitrary size length. When I want to test it with length 5, I set it to 5. When I want to test it with length 50, I set it to 50 and so forth. It's still static, it's still compile time. It's a little bit more flexible piece of code. This piece of code we have here on the bottom is an important thing to consider. There are 3 different ways when we declare our arrays that we can actually initialize them. First is when we declare the array, we can be very explicit about the length and about the elements inside that array. So here we declare an integer array just called myArray of size length, where length was defined to be 5. And in those curly braces, then you can specify those are going to be the elements that initialize my array. We actually, if we're going to fully initialize the array, we don't need to actually explicitly declare the length of the array. So you can actually omit having the length of the array, and this is still syntactically equivalent to this first example up here, where we're just specifying that there's 5 elements. The compiler is clever enough to determine that you've initialized with 5 elements, your length is going to be 5. I don't use that example as much in my own code, for the reason being that if I'm going to initialize with 5 things, I need to know the number 5 in my code anyway. I need to know the length to be able to work with that array. We might as well be explicit when we do that initialization and say, yes, this is an array of length 5. It's not an arbitrary size length. We know exactly what it is. Our code needs to know length anyway. Might as well add it there. The other approach is a little interesting, in which if you declare the array to be of a certain length, of course you don't need to initialize it at all, but you can partially specify the initialization list as well. And you can say, I have an array of size 5, as the example here is showing, and I'm just going to declare the first two elements when I do that initialization. 1, 2, the remainder of those array elements will be initialized with 0. That can be something that you would commonly want to use. I have to be, technically upfront with you that C does allow support for variable length arrays at runtime, where you declare, for example, my array of n, where n is an int that's determined at runtime. It's a little compiler dependent, and the reason I also don't want to use that is when it doesn't work for our purposes, that can be very hard to debug the type of errors that we see. So we're going to start with statically defined arrays. That's going to work for a lot of our programs for the next few weeks. We'll get to proper dynamic memory allocation. That raises its own set of programming challenges, but at least it's something we'll be able to track down and debug when we do have those challenges together. The memory view of our arrays is pretty important here. I can't overstate this, I think, enough that we have to be thinking in these terms when we're accessing and creating arrays in our programs. Arrays are located sequentially in memory. So if I declare a double named resistors of size 100, I'm declaring 100 of those doubles. Doubles happen to be 8 bytes wide. If we're not sure of that, we can always use the size of macro to declare to calculate exactly the size of that, but it's 8. It's going to be 800 bytes of memory we're allocating for that double. The other key important aspect here is, and other programming languages do this differently, is that when we declare an array of length n, the valid subscripts for our code is 0 to n minus 1. If you try -1, you're going to have a hard time. If you try 1 to n, you're going to have some really subtle kind of bugs that are going to be hard to track down. You have to keep that straight in your head when working with arrays. And frankly, if you do keep track of that while working with arrays, you're pretty far along in terms of understanding arrays in our programs. There isn't that much more to it than just keeping track of the subscripts for our arrays. Let me just say it one more time. If I have an array of length n, my valid indices or subscripts are the range 0 to n minus 1. We were looking back at our for loops where we were declaring for int I equals 0, I less than n, I plus plus. That I value is going to be perfect for our subscript for that reason. Because as we start for I equals 0, we go to I equals n minus 1. That'll be the exact right indices to subscript our array to make sure we've actually accessed every single element in the array and nothing outside of that in the memory range. The compiler will let you do it. It'll let you say array of, in this case, or resistors of 101. What result you'll get, whether your code will crash, whether you'll just get some weird result, is not something that the C specification itself tells you. It's really dependent on the system that you happen to be running it on. Your code and the person's next to you code could in fact give different results. So we really want to avoid that when at all possible. So again, if I have an array of length 100, I declare array size 100, 0 to 99 are the indices that work. Don't access it with any other index. But beyond that, that subscript can be anything else that's valid C. All of the examples I show down here, and then I'll show the code, it's called array fun, whether it's fun or not, depends on your perspective. All of this is perfectly valid ways of accessing an array. So we've declared our array, and it's going to be of length 5 because we've initialized it without specifying a different length, and we've initialized it with 5 elements. A constant subscript is perfectly fine. Again, as long as it's in the range 0, 1, 2, 3, 4. You can't do y of 5, that would be wrong. Y of I, where I is some other integer variable, is also an extremely common thing. And we'll see lots and lots of examples. Your programs will all be doing the equivalent of y of I in your code. In this case, I is set to be equal to 3. We would be accessing the element not 0, not 1, not 2, not 3. But 3, excuse me. We'd be accessing the value of 1 here for our printout. You have to keep that straight in your mind. And once you do, you're in really good shape with arrays. Y of 3 is the 4th element in that array. So any specification for a problem has to be really clear what you're actually trying to request. Y of 3 is the 4th element. Y of I is the I plus 1th element in that array. We're starting with 0, so the subscript name and which actual element of the array is always going to be differing by a value of 1. Other programming languages go from 1 to n, and there's less of that issue. C starts at 0. Can't say it enough. We can also do any sorts of expressions. Y of I plus plus. Of course, you never need to have a complex expression like that, right? You could always access y of I. This is the postfix incrementer, and then do I plus plus afterwards. There's nothing forcing you to combine lines of code in that way, but you'll see this in examples. This will still print y of 3, and then afterwards I will then be equal to 4. We then can also do just complex things where we actually take the value of one array or of its own array to create an index for that or some other array. It's harder to think of examples where we'd want to necessarily do that. One of your programming practice examples that may wind up being the way you implement it. It's looking at letters being input. You probably want to create an array of size 26 to store how frequently each letter is being found. And you can do those via some pretty quick tricks where you grab the index of the letter, you use that to create an index for this array of counts. At least that's how I would implement it. So this would be valid C. Now this example here is pretty frustrating because conceptually, it's wrong. We have I that is a value of 4 at this point. We're doing y of I plus 2, and this value is wrong because I plus 2, it would then be equal to 6. Even if it was equal to 5, that's still wrong. 0, 1, 2, 3, 4 are the only valid indices. When we actually try to run this, it should give us a warning, right? It should give us an error. It should tell us that, hey, something is bad here. But when we run this, when we compile this, we get no warnings. We get no red squiggly lines that we've become so accustomed to in our replit environment here. C thinks nothing is wrong with this, and by spec, nothing is wrong with this. But we're getting this value that just so happens to be 0. There's absolutely no guarantee the actual value is 0. I don't want to mess around with it too much, but I think with a little bit of effort, I can probably make it print something else out instead of 0. In this case, it's still 0. Let me try one more thing, and then I'll give up. It really depends on the runtime environment. You have no guarantees what'll be at that next location in memory. Still printing 0 here, so it's doing something reasonably clever to avoid this being an issue, but it's still not correct from your program's perspective. Y of 6 or 5 or 23 is wrong. It's going to lead to a crash. It could be that this system just initializes enough memory in 0 in all directions that it doesn't cause you any problems. That's a really big number. We try a somewhat smaller number. Still printing 0. It could be smart enough that it's just detecting this is out of range in the runtime and just giving you zeros. But still, it's wrong code. It's not code that is the result that your program would be expecting. If you operate on that value, y of I plus 2, it's not crashing as we're saying. It's not going to be right. Your result isn't going to be correct. We've covered for loops. I know we're not experts in it yet, but you worked on some programs with for loops, and we'll work on more together today and in the next lecture content as well. But they're really a natural fit, and they really were designed hand in hand. We have for loops that have these loop index variables. For int I equals 0, I less than n, I plus plus. And we have these arrays that are potentially of size n, for which the valid indices and subscripts is 0 to n minus 1. So as we go through our for loop, accessing each element in array in turn is just a very natural thing, and we'll just see that code pattern over and over and over again. Let's say after declaration we wanted to declare this array z, and then eventually initialize it with a set of squares, right? 0, 1, 4, 9, 16, 25. You can always manually do it, right? You can always say, okay, z of 0 is this, z of 1 is this, etc., and just kind of hard-code it in there. But we can kind of see the pattern there, right? It's 0 squared, 1 squared, 2 squared, 3 squared, etc. If it's 5 values, no big deal. If it's 5,000 values, that becomes a big deal. We can do that in our for loop, and this kind of design pattern is going to be so common here. This is an array of length. If I said 5, I was wrong. Array of length 6. So I equals 0, I less than 6, I plus plus. Z of I equals I squared, or I times I. This now becomes part of our problem-solving process, and I want us to work through an example together. We are always thinking as we're going through the problem-solving process of what is our data, what variable data types does it need to be, and we're still doing that when we're talking about arrays here. But now we're really thinking also in terms of, okay, what data do I have? What arrays make sense to store the data I'm going to have for my program? I think for a lot of these programs, not just for this topic, but for the next topic and the one after that, in some sense towards the end of the semester, if you can answer that question of What array does my program require? And as I mentioned, the loop and the array are just these naturally kind of connected concepts. If you have an array, a loop is the right way to access either for reading or updating an array. So if we can think of what the right array is for our program, the rest of the code, I'm not saying it's easy. None of these programs are going to be easy starting at this point, but there's just kind of a natural connection between the data I've declared in my array, what for loop is the natural thing to create next. It doesn't solve the problem for you, but it gets you a decent way along the way. So this problem is a pretty conventional problem of writing a program that reads in a set of midterm scores. And fortunately, we don't have a midterm in this class to stress out about. Reads in a set of midterm scores and no more than 50 scores. That's the first kind of light bulb that should be coming off, and reports back the class average on a scale of 0 to 100%. So for example, if the midterm was 60 points, then after 45, 47, 35, 53, the program should print out 75%. Another, I would call this a simplifying assumption that makes the program easier, not harder, is that after entering -1 for a value, there are going to be no more scores to enter. I don't expect you to know this immediately off the top of your head, but when I read this description, I wrote this description, but when I also, in fact, go and read this description, the two things that really come to me, the light bulbs that I see are no more than 50 scores. That's important. There's going to be no more than 50 scores. And I'm also kind of telling you that, by the way, we're limited to kind of static memory allocation for keeping track of our scores. And I also mentioned, hey, if you can think of what array makes sense, you've made a lot of progress in solving the problem. If there's going to be no more than 50 scores, what I would do first and what I would want and hope for you to do first is say, hey, we need some variable to keep track of the number of scores in our program. That's the first mini light bulb I want to see eventually here. The other kind of mini light bulb, I guess, would be, after entering -1 for a value, there are no more scores to enter. So you can implement this, as we've seen, in one of two ways. It's going to be a loop. It's going to be between 1 and let's say 50 scores that are getting entered here. With a while loop, that makes some sense, right? While current score does not equals -1, continue. We can also do it with a for loop where we explicitly break out of the for loop when this condition is met. One approach isn't better than the other. I guess my bias or my inclination would be, hey, I have this problem for which I know there's upwards of 50 things. So I have this loop where I can say, hey, this loop, I know a lot about it. And because I have my array of size 50, I know that I have this for loop that's going to go at most 50 times, iterate at most 50 times. If you have that array of size 50, for loop of length 50, I know that the problem isn't solved for you yet, but you're pretty far along. I would add a comment now here that I need to actually read in the scores, and that's what I would do first. A lot of these programs that we have, the first challenge is kind of data input or data entry or just getting the input data, whether it's later from a file, from text that's typed in, or from other sources. We need to do that here. This specification isn't as tight as the ones for our programming practice, but we know we need some sort of prompt. Let's say enter midterm score, and I think it'd be useful to kind of keep track of which score we're currently entering. Always add that nice little space. That if we used I, that would kind of start at 0, and that sounds weird, even though we know that's what the array is doing. So let's print out I plus 1. So enter midterm score 1, then enter midterm score 2, then enter midterm score 3. By the way, the program doesn't do anything yet. No harm in running it. Well, I see a partial issue here, but that's because we're not pressing enter on scanf. All right, it's printing out 50 prompts of enter midterm score. We also then want to do our scanf. Scanf %d. We haven't really covered the syntax for what it means to read and provide the address for an individual element of our array. The correct, for what it's worth, the correct syntax would be that. I want the address of the variable I want to overwrite, and the variable I would want to overwrite is scores of I. I feel like that's not cheating per se, but it's also something we haven't really covered, and your other programs don't really expect it. But what it is perfectly valid is to have some like temporary score or You can call it current score or something like that. Just another variable, maybe current score or something like that would look a little bit better. So we're making it clear it's not the same variable as our scores variable. Enter midterm score I plus 1, read in current score, and we actually only want to update the scores array if that score is not -1. If it's -1, actually, what do we want to do, right? If current score is equal to -1, I think a reasonable comment would be, well, literally what it says. After entering -1 for a value, we are done, or there are no more scores to enter. We have this for loop that by default is going to go 50 times. We've just detected that actually we're done, and we don't want to be entering any more data. That's a good use of that break keyword. Again, we could have done this with a while loop, and that would have also been totally fine. But I know I have this length 50 kind of as a constant here. 50 values, iterate 50 times, but then get out of it early. For me, that's a good use of the break keyword. But otherwise, this is a valid score, and now we can update that array. We have our array, and scores of 0 is the first one we're updating, then scores of 1, then scores of 2, etc. We also probably, although this is not necessarily inherent in the description of the problem, we also really need to keep track of, how many scores did we actually have. This int I would have been okay for us, and if you tried to use int I right here, you'd have a compile error because of that scoping thing we've talked about. I personally don't like using I for anything other than our array indices and our loop iterations. I would just recommend separately keeping track of, score count or total count. How many valid scores did we actually keep track of? Yes, I know that would be technically equal to I minus 1 at the end of this loop, but now we have a variable that has scope of outside the loop. We'll be able to print out how many scores we received. In fact, let's just do that. %d scores, I don't know, received or something like that. And, testing this is, of course, a little bit of a pain. Let's say you got a 50, a 60, and a 70, and then that -1 is what's ending it. 3 scores received. We basically have the problem solved, although there is, of course, then a little bit of math. We report back the class average on a scale of 0 to 100%. If anything is asking you to calculate an average, we could start with the sum, right? Maybe a little comment, hey, we have count. Count now holds the valid number of scores. Int sum equals 0. Now we got to go back through that array. You can use I again. If you're not comfortable doing so, use something else. But now it's not I 0, I less than 50. It's I equals 0, I less than count. And now we need to do some accumulation. Grab each element of the scores that are valid, because -1 did not get stored, add them all up. We then need to actually calculate the average, sum divided by count, and if little tiny alarm bells just went off in your head with that line 39 of this code, you're in great shape. Slight problem. Very slight, but you would see it in your test cases. Sum is an integer, count is an integer. If we're just doing integer division, we're going to get truncation, rounding kind of errors, right? You can promote it by including 1.0. You could cast either of these to float, and you should get a good result. I would say syntactically that's probably the right way to do it. And now let's actually print it out correctly instead of %d scores. The average for the %d scores was %f. We already have that. %d scores, that many scores, average. Let's print that out. Let's do 50, 60, 70. Oh, and then -1. The average for the 3 scores was 60.000000. What did it want to print out? It looks like 75.0. Oh, and that's annoying. With the actual percent sign here, well, we print the percent sign kind of annoyingly by %%. So that would fix that part. It looks like it's showing just kind of 1 digit past the decimal point. We can tell our floating point print, hey, print this floating point, but only print 1 digit past the decimal point. Let's actually enter in those numbers and make sure our math is correct. So 45, I don't know why it would print out 75%. Oh, if the midterm was 60 points, well, but we don't know the midterm is 60 points, so that's kind of a flaw in this specification, isn't it? Well, that didn't really say. That's our sum divided by, you can say count times 60 if it is out of 60. Didn't say that, or wasn't that obvious that that was the case. 45, 47, 35, 53, -1, 0.8% sounds great. If it's going to be out of 60, we divide it by the total number of points. You can just multiply it by 100 to get an actual percentage back out. Oh, let's type this in again. One final time, 47. If you only struggle this much on your programming practices, you're in really great shape. 75.4%. Sigh, because I typed it wrong. 45, 47, 35, 53, -1, 75%. We have, it says example, if the score midterm is 60 points, we'd have to spec that a little bit tighter. It's the same calculation. I just assumed when we were testing it early, it was out of 100 points. So it was kind of dividing by 100 and multiplying by 100. So you didn't need to do either in that sense. So that's our use of arrays, and frankly, that's really it. I mean, if you know that about arrays, and you know that my problem I'm trying to solve, I need to have some defined array, and for our cases, we're going to want to have some fixed length array that we're defining. Could be some pound defined, but still it's size 50 or size 10. And you should recognize that your code is going to have one or multiple for loops of that same length. You're so far along in actually solving the problem. Yeah, there were some subtleties there, right? In terms of how are we calculating an average? How are we keeping track of how many valid things we've received? But if you can think about your data that your problem requires, think about what looping structures it requires, and then of course what control cases we need to also consider inside that loop, you have the problem solved, and you're just kind of wrangling with syntax and testing, as we saw in our example here. We'll move on to the next topic really soon here. I'm going to cover a little bit more about arrays in the next video with a little bit more applied practice as well.